Welcome back, everybody. We're going to conclude our discussion about Markov chains today. We will be coming back around to it and doing an actual proof on the algorithm that I'm going to show you. I'll show you what we need to show, essentially, and I'll give you some more tools, mathematical tools on how to show these things and what typical proofs look like. We're not going to do it this time. It's pretty mechanical, like most proofs. If you ever read through typical theoremist papers, it's all the same stuff that everybody else has ever done. It's pretty templated, is the way I think about it. There's a couple techniques. When I took real analysis once upon a time, I figured out everything boiled down to 3 different techniques. Triangle and equality is probably one of them. Heine Morel, within covers closed and bounded spaces, blah, 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 blah. Same stuff happens in statistics. So it's we're always studying the boundary effects of something, and things cover things in the right way, and what happens with the tail behavior. Saying that, the proofs don't have to be measured theoretic, I don't think. So I'll show you some kind of calculus-driven proofs. I kind of like those. Anyway, let me just recap. One recap before we recap. Friday is fall break, no class. Enjoy the weekend. Monday, Sierra's going to give a lecture. I'm going to sit off to the corner in the side and pretend that I'm reading or something like that. So let's give Sierra a pleasant welcome when we come back. She's going to teach you about Jeffrey's priors. Basically, it's 5 lines of stuff you need to show. So it's kind of a little bit mathematical. If you guys get a chance, go to Wikipedia, go to your book, go to any of A's books. It'll be in it. So it's in your book by Peter Hall. Read through it, see if you understand the calculus and how derivatives get pulled out of expectations and how Houdini's is being applied in those sorts of examples. You need to kind of understand properties of expectations and log likelihoods as well. If you know that standard stuff from basic inference class, so I mean kind of grad school basic inference class, so some of you haven't had that, you might know some properties of expectations of log likelihoods and stuff like that. But basically, it's a bunch of calculus you have to work through. And there's a few identities that if you're familiar with, proof's not too hard. I'll probably come back and I'll say something about other classes of invariant priors and why we choose Jeffrey's. That's going to be beyond the scope of Sierra's class. So I'll say this, what she's about to show you, the thing she's going to derive has a certain property in that is not unique. You can come up with it in other ways that are not good. So I think that that's a little bit steep for this class, but Jeffrey's priors, read through the little math thing that says those priors are invariant priors and understands what they mean by invariance. Invariance with respect to what? And in this class, it'll be with respect to transformation. So anytime somebody says the word invariant to you, it means nothing until they tell you what they change and what doesn't change. So they move something and something stays the same. Invariance. So what are you moving? How are you moving it? What's the mathematical concept there? Okay, we'll do review tomorrow, 5:30. Is it 5:30 or 5?
5:30. We pushed it back 30 minutes.
Please send some questions or topics or things you want me to talk about. If you can get me going, I'll unleash other problems and examples, but that's what that session is about. So I'll be around for about 2 hours is about the average, but it could be shorter. If there's no questions at 5:25, I'm gonna go for a motorcycle ride. So please try to send those over to the Slack page. You all have access to that. Okay, let's just run through these concepts real quick that we learned about. I wrote down something more technical. This is what you would see in the textbook for aperiodicity, and you have to chew on it for a minute. What the heck does this say? So aperiodicity for Markov chain means that every state has period 1. So not 2, where things cycle in that example, where I gave you the kind of backwards diagonal on the identity, the non-identity looking thing where the diagonal runs the other way. You can see that just flipping states all over the place, sending you to weird places. that had a period too. So this is what the more mathematical statement is, and there's corresponding statements that go with this. I kind of like it in English so I can understand what it all means, and then I like to be able to write down things technically. So for the other group. The period of state, you could consider this continuous or finite. So this definition works regardless of the nature of X. It lives in some space. So in math, they'll always tell you what the space is that we're talking about that things live in. So this is going to be the space for whatever that thing is, that random variable. So random variable being the state in this case. So this is the period. This is the greatest common denominator. Greatest common denominator. If you're a math major, this is how you talk to people. So in this set notation. So what I have is I've got those curly braces. It says the set of numbers right here. These are the positive natural numbers. We start counting at 1, 2, 3, 4, 5. That's what that says. So, so natural numbers, counting numbers. A lot of technical nuance. The positive thing right there says not including 0. We're counting steps in our Markov chain. So these are just the steps, the numbers, the counting numbers, and this always means such that. So this is the condition. Luckily for us, that's about the same notation that we use when we write down posteriors in this class. We just use bar. So we're conditioning on something being fixed. So this is the set of natural numbers such that this is true right here. So this is the transition probability, t to the n. So transition probability. Such that they're all greater than 0. So what it's doing is in this transition and it's figuring out how often you can return to a state. When it's a 0 in the transition thing, you can't get there on that step. So that's what they're showing you right here. They're looking for all the different steps you can come back on. So that's what this set is going to be. And you're looking for the greatest common denominator of it. So if you had something that looked like you could only arrive back on 2, 4, 6, 8, it would have period 2 if that sequence continued. However, if it went 2, 4, 6, 8, 9, 10, 11, 12, 13, 14, 15, 16, and it continued like that, after a while, I can get back on any state. And the greatest common denominator between all of those numbers will be 1. So states have periods, and if the whole Markov chain has period 1, then we say that it's aperiodic. Okay, so you have to kind of evolve the Markov chain for a little while and see what steps you can come back on. If it irons out and it starts becoming a sequence of just the counting numbers, it doesn't have to start that way, then we say the thing is aperiodic. Turns out it's trivial to take any Markov chain, and make it aperiodic and preserve the stationary distribution. So all you do is you add a little bit of probability to returning to itself on the next step. So that's called self-loop. And I can get back just to myself on the next step. If you add the same probability to everything, just a little bit, it preserves the stationary distribution. That's kind of cool. So for a Markov chain applications person like me that I work with MCMC, and I want all of these conditions to work, making them aperiodic is quite simple. I never actually do that. I just make sure I have a proposal distribution that covers all the possibilities. So really, it's all very technically nuanced, but I think to understand the future proofs, we have to understand some of these concepts. Irreducibility says that every state can reach every other state. So you don't get trapped. This right here means communication between states. So this is what is said to communicate between states. So if you read through, and I kind of glanced at my Markov, my own stochastics books, they usually pile on a bunch of definitions before they get to the real definition they want to give you. So they'll talk about each state communicating, blah, 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 talk about properties of that, and then say if every single one has that property, all states, then it's irreducible. The counter to this is getting trapped in a space, and you can never leave that space. So then we say then those states are transient, we can't come back to those states. So that's the opposite. Positive recurrence says the expected waiting time for returning to each state is finite. The opposite of that is it takes forever to come back. Doesn't mean that the probability is zero, it just means it's highly unlikely. That expected term is what they mean, so it's in that sense of expectation. If you don't know that expectations are sometimes a little bit strange, just think about things like Cauchy distributions. So a lot of things don't have finite expectations, like problems like that. Counterexample to this would be the autoregressive process, where I took my leading coefficient on the term that I'm autoregressing on, and I make that bigger than 1, or less than -1. That Markov chain will just run away. Stationary distribution in that Markov space doesn't even exist. So for the other ones, for things like the aperiodic stuff, a stationary distribution can exist, but a limiting distribution does not. So, fun things to think about. So stationary distributions don't even need to exist, but you would never be running Metropolis-Hastings on something where a stationary distribution didn't exist in the first place. So you can try to run this algorithm that converges to something stationary, but the process is running away from you. All you'll ever do is chase it. You'll never converge. That makes sense. Limiting distributions, we talked about that. So it's really, in the discrete sense, you're building up your Markov transition matrix. That's my transition matrix. As I power it up to the nth power, that's the n set transition. I look at the ij element, and if for all I, everything just depends, it's the exact same number, and it doesn't depend on I. So if this thing exists, basically all of those columns of your Markov chain are converging to the same number. You can see that in something like an aperiodic Markov chain, that might not happen because it's just going to keep flipping around. It's not converging on that step. There's zeros that appear on certain steps. Go back to the top definition and kind of see that they're talking about non-zeros. You can think about non-irreducible Markov chains where you get trapped in that space, and that's not going to converge. It's going to depend on where you started from and the trajectory you took. And so you might get trapped. So those are kind of the cases where limiting distributions don't exist. Stationary distributions, hopefully you guys chewed on this a little bit, but this was just this. A transpose, so this is the transpose of the Markov transition matrix. Remember the PIJs? They mean that I'm starting in state I and moving to state J, but in probability space, we condition on I first, and then we move to J. That's where the transition is coming from, or the transpose is coming from. So this is just that system of equations that we wrote down last time. So this is going to be my stationary distribution. So you can do things like this. I can say A transpose minus I pi is equal to 0. Same sort of thing might be what Mohammed was thinking about last time. I just multiplied the right-hand side by the identity and subtracted everything over and factorized out to pi. And so I could try to do a linear solve on this system and figure out what pi is. Not too hard. Keep in mind, we need the constraint also built into the equation. I need everything to sum to 1, everything in that pi vector. And I can very easily include all of that right here. So I'll let you think about this system, but if I just put in a row of ones down here, and I cut down a 1 right there. These are all scalars, so I just put down a row of ones. The pi is factorized outside, so I have pi times the vector of 1s. What is that doing? That sums together all pi's. And then I say it's equal to 1. So I can actually do a linear solve and figure out what this first eigenvector is. The advantage is that I know that there's an eigenvalue of 1 in this system. How do I know that? I took my Markov chain class, or I've done it on a countless number of examples, and there always was 1 there. Martin?
Just one curious question. Are you putting the last row of the last condition of all the pi summing up to 1 because otherwise it will be in the result? Or
Because I can't consider things like negative pi's. I can't have things that don't sum to 1, so I need to say I want pi's. Keep in mind, eigenvectors I can multiply by any constants. And they're still an eigenvector. So, so I can stretch those things and do stuff like that, and that breaks my rules of probability. So I need this to conform to something that's a probability. And just write it down a little bit more clearly here. It's a fudging for space. So this is just A transpose minus I, and then I have a row of 1s. We'll write it like this. It's the identity. So here's my matrix right here. Multiply by pi. This is going to be my vector of zeros over here. So I'm going to write this down as a vector of zeros, corresponding to everything in this top thing. That's a whole system. And then I have a little scalar down here. So if anybody gives you a Markov chain, wants stationary distribution, it's not too big, it's discrete, you can find the stationary distribution just by doing something like inverting that matrix. But again, they will check your MATLAB accounts. And if you actually write in, you're out of here. So they do something like a QR factorization, some sort of LU factorization. If you don't know about that stuff, take a numerics class, it'll always serve you well. They're practical, they're fun, you get to do things, project heavy usually. But stability in computing is something, if we're going to get into MCMC, we need to be aware of. Okay. In the continuous case, just write this down. We'll give you a continuous analog for stationary distributions. And this is the continuous case. It's the same thing. So there's an integral instead of a sum. It does make the math harder, obviously. So we'll see what we put in here. But I want this thing to be equal to pi x. So this is going to be my continuous stationary distribution. So continuous if you're writing a paper, I can tell you where x lives. It lives somewhere. We're not going to change that throughout the problem. So you can glorify the notation if you want. What we need is the continuous transition. So, and I'm going to say this is x given x prime. I'll change what I integrate over real quick, and I'll say this is pi x prime. So this is the same function. Integrating over x prime. So these are just two different spots in my continuous space. If I just wrote down whatever this letter is, that I call it a row. And I think a lot of people in the Markov chain literature call it that. But this is my transition. So I don't say probability if it's continuous space, it's a density. So a lot of times these things might have mixed components in them too. You might have something of a discrete nature and something of a continuous nature in your problem as well. I'm specifying everything's continuous by writing down integral. Sometimes I just write down integral when I mean some. And I say, I didn't tell you what my measure was, how I was counting. There's a lot of different types of integral. Here I just need a name of them. So this is the transition density. This is the stationary distribution as well. Here. So they're just being evaluated at different spots. So what this says, when I think about this integral, is that if I draw, think about our sampling schemes, what this integral means. If I drew from the stationary distribution, I grabbed the state, I pushed it through my transition. So this is a Markov transition. Then I get back to the same distribution, just located at a different spot. So let me write this down. It's a two-step process. This kind of smacks of a lot of things we've seen before. I could sample from this. If I knew how to sample x prime from pi x, so I'll just make that a dummy variable, but now I've got x prime out of it. And I take my transition density, so this is a Markov process, so it's something that's random to us. And I take x prime and I plug it in there. And I'll give us a little bit extra notation. I'll say this is x double prime. Then I draw from that. If this was stationary, this part, and I'm saying that it is, then I know what distribution governs that point right here. This is also effectively coming from the stationary distribution. So that came from the same distribution that I drew right here. So that's what it means to be stationary. So if I'm drawing the first initial state, and that's what stationary distributions are all about, is saying, let's randomize the first state and see where we go. So in that example where I have ones on the diagonal in the opposite way we usually think about, then there was some probability of being in that state, but I kind of had to randomize the starting location to think about it. Alice?
Does the transition density have anything to do with the transition matrix?
If it were discrete matrix.
Or if they are discrete, so they are matrix?
Right, so I'm talking about a continuous analog. So this really is the same thing that we wrote down before. A transpose pi, where that's now a vector, is equal to pi. So this equation is the same to me. So I've got a big sum going on in there, which you can't see in my matrix algebra. So I'm just doing the exact same thing. So what this says is if I start with a random draw from the stationary distribution, I move through the Markov chain, we wind up in the stationary distribution. So once you're sampling from the stationary distribution in a Markov process, if it exists, you stay in the stationary distribution. That's what Markov chain Monte Carlo does for us. So we'll come back to an example in just one moment. But anyway, I like to think about it this way. This is kind of a hard math problem to solve. It can, in general, be pretty hard to do. And so what some people do is if they can at least write down their transitions, and they know that the chain doesn't get stuck anywhere, it doesn't have any funny cycles. They don't drift off to infinity. I always come back. Then I can run the limiting distribution and achieve the stationary distribution. So here's what I said last time, that if these three conditions are true, that the chain is aperiodic, it's irreducible, it's positive recurrent, then these two things are the same. So if 1, 2, and 3 hold, 1, 2, and 3, then star is equal to star star. So that's our code. Don't talk to people like that. Well, I need 1, 2, and 3, and then star is equal to star star. People come into my office all the time, and it's like, you're going to need to tell me what it actually is. But if the chain has these properties, then the limiting distributions are stationary. And so we're not going to work with limiting distributions that don't exist. Markov chain Monte Carlo is iterating through a limiting distribution until it becomes stationary. Let's do an example real quick so we understand how this works. Then we'll go back and we'll look at my code, and I'll tell you what it does. I also want to slot one thing in here, and this will go without proof in this class, and maybe we'll write down the proof for me. So why Gibbs adheres to the same mathematical thing that just Metropolis-Hastings does. So I'm going to tell you something that might be surprising, and later on we'll justify that we can do it. So Metropolis-Hastings is step 1. We propose. So I'll say propose. So what I'm going to do is I'm going to draw from some distribution. This is going to be my proposal. I'll write down what we're trying to achieve. Goal, sample from some distribution. I'll call it pi x. And pi x, in our example, will be stationary. Our Markov chain will be convergent to that. So this is like the one and only time I don't flip my notation right in the middle of the example for you. So 2, then we do something. We compute alpha. This is our decision rule. We'll write down that we decide. And I probably should put what I'm transitioning between right here, but it's not standard practice to do it. So this is the minimum between 1. This is going to be a probability. I take pi, theta, write this down as my proposal, theta star, and I'll compare to where I was last time. So I need to introduce the initial step so this thing actually runs. Initialize. Theta 0. So on my first iteration, I have something to plug in there. That's our starting point. And of course, it makes a difference. In practice, if you start real far from the answer, and you have a poorly mixing MCMC scheme, it'll take a long time to converge. In theory, I could give you one algorithm probably and say, well, technically it converges, but you're going to have to wait until the planet Earth doesn't exist anymore for this thing actually to work. So we need to do better. And then I need to build in my ratio of my proposals. This is my inverse ratio proposals. And then I make my decision. So I'll say theta t is going to be equal to one of 2 things. Where I was last time or where I propose to move, and this will happen with prob alpha. And this happens with prob 1 minus alpha. So this is a Bernoulli coin flip. Flip the coin, decide which one after you compute this probability. In our Bayesian applications, this is a posterior distribution. And the nice thing about it is all you have to do is write down likelihood times prior. You don't need to normalize it. If you go through the effort to normalize it, you probably could do this exactly. So you can probably get all this stuff right without running a sampler that eventually converges. I'd love to have samplers that sample fast, and by eventually converge is instantaneous. I'd like that. That's what MCMCers are working on. So for particular problems, they're developing proposal schemes that get you around the space fast. So if this proposal covers the same space that pi lives in, pi theta can change the argument. So pi theta is our stationary distribution. I like sampling thetas. I'm always sampling thetas, the parameters, and not the data, because I'm a Bayesian. So, in most applications. Okay, so that's the algorithm. Whole name of the game is pick a proposal that works reasonably well. Let's give you a simple example, just to write down an algorithm that you would go and code up. Now, this is a pretty poor example. And the reason why, so I want to sample from this posterior distribution, and you might have some context for it. I will never plug that into my computer. We'll talk about practical issues of computing as we go. It'll probably be more relevant as the homework becomes closer to being due. We'll be like, doesn't work. I think it's right. I worked out the algebra. It's like, yeah, but there's more issues. So this is just a normal posterior problem. So I'm just sampling x's from a normal mu sigma squared. I'm saying that we know what sigma squared is in the analysis, and I've used the flat prior. That is Jeffrey's prior for this problem. It's got a lot of other properties we talked about as well. Sierra will clarify that on Monday. Or Wednesday. Probably take 2 days. We'll see. So this is a horrible problem to run a Gibbs sampler on. Or sorry, a Metropolis sampler. I guess technically it's Gibbs, but in the most uninteresting way possible. There's only one parameter. Why is this a dumb example? Because I know mu is distributed normally with mean x bar invariant sigma squared over n. Because I can do the math. And so all I have to do is sample from normals to do this. But if I didn't know that, then maybe I could do something else. Maybe I had facilities to sample from a normal, although I don't recognize that as a normal, so I don't know what to do. So I'm going to give you the worst example ever, but it'll at least drive home some points for us that we can look at. So what I'm going to do is I'm going to initialize. So 0. I'll take mu 0 and plug something in for it. Usually just write that down. Boom. It's that thing I picked it. Step 1, I'm going to run this through a loop. And I always close my notes as soon as I open them. That should be something you always do. So you open a loop, close it instantly. I've just saved you days. So, or you can waste those days and come back running this. So, if you're one of those that likes to open your loops without closing them, you're oftentimes looking for that, and that always gives you a horrible error that it's hard to find. So, anyway, same is true in LaTeX. I've noticed that's like the worst compilation error that you can have. It's an open trace. I have 2 steps. So what I'm going to do is I'm going to propose, and I'm going to show you a particular type of proposal in this example. So this does have at least something going on that's kind of fun and interesting. This is really why this is the worst example ever, is I'm going to use a normal proposal to do this. And this is a typical proposal that most people use. If you've got a nice continuous space, unimodal, these are typically the proposals people will use. Why I don't like this example a lot is because I know that's normally distributed, so if I can sample from this, I can sample from that. So the idea is that you can sample from this, but you don't know how to sample from that. Now, it is possible that I know how to write down likelihood times prior, I just can't do any math. So I'm like, I don't know what to do, but I do have this normal sampler, and I know that mu is continuous, it lives between -infinity and infinity, and I know some distribution to sample from that. So even if you didn't know the correct thing to do, you could still use this. And I think a lot of people do that. So I'm going to center this somewhere. I'm going to take my old value. Oops, did this again, right? So changing the notation. Let's go. Step 1 is mu star. comes from G. So let's stick with the same random variable. So G is going to be equal to, so I'm going to let this be normal, where I was last time, and then I'm going to put in some variance right here. We'll talk about this. This is your tunable. You tune this. What does this thing look like? This is 1 over 2 pi, square root, psi, e to the minus 1/2. This is going to be mu star minus mu t minus 1 squared over psi squared. So what I'm going to do is when I propose everything, I'm going to say, I'm going to center my proposal where I was last time. And that's fair game. So you're allowed to do this. So I can guide myself based off of what I thought was good last time. In my code example that moves really slowly, so you can see it, what I've actually done is I've taken psi and I made it really small. So I can only propose a little bit at a time. So you can watch my code converge. So I have a very clumsy implementation and poorly tuned implementation, so you can watch it converge slowly. So this is kind of cool. I want you to also notice that this function is symmetric in mu star and mu t minus 1. What I'm going to do is I'm going to write down the acceptance probability. So acceptance probability is going to be min 1. And now I've got my thing right here. I'm not going to normalize it. I'll just plug it in. So I'll write down pi. Pi equals 1 to n. E to the minus 1/2 xi minus mu squared over sigma squared. If you want to multiply by 1, I can do that. I goes from 1 to n, e to the minus 1/2 xi minus mu squared over sigma squared. Got to plug in which mu's these are. This is going to be my proposed mu, and this is going to be my mu t minus 1. So I proposed a new value, plugged it in there. I have my last location on the first step, and plug that in right here. So I'm taking that ratio. There's something else I want to do. I want to multiply by the inverse ratio of proposals. But I just want to point out that this ratio of the target functions right here is basically saying if mu star achieves a higher likelihood value, or proportional to the posterior in this case, the likelihood is proportional to the posterior, then probably make that move. It looks good. But if mu star is inducing a smaller likelihood function than mu t minus 1 is, it doesn't say don't make the move. It says make it with something to do with the ratio of this. Now I want to point out this term right here, G, mu star, or I'll say mu t minus 1, given mu star, this would be G mu star, mu t minus 1. It's actually very easy to compute. So my inverse proposal, it's being evaluated in terms of the random variable right there, but I have to condition the exact same way that I would go in both directions. So this top part is saying, how often do you go backwards? This part right here, the way I proposed everything, so this is going to be mu star given mu t minus 1. The way I proposed everything is it was centered at mu t minus 1. What the numerator is asking you is how do you move backwards? How would you have reversed this move? And it's very easy. I would have centered it at my proposal value and tried to move backwards to the old location. I've already said that this is symmetric in these two arguments. So in this example, this is 1 right here. If you plugged in those two densities, they cancel each other. That's what's called the Metropolis algorithm. And so the Metropolis algorithm happens when this thing is 1. I call the Metropolis-Hastings thing the Metropolis thing. I often will just say MH, who knows what I'm saying. I've never heard anybody say Hastings algorithm. So for Hastings, sometimes Metropolis gets all the glory. But this is Metropolis, technically. Metropolis wrote a paper. He had a symmetric proposal requirement, so it doesn't mean it looks geometrically symmetric. It's symmetric in your arguments. Where you were last time and where you're proposing to. When that's 1, he worked out all that for that. Hastings came in 3 years later and came up with something more general. I think this is awesome because every MCMC algorithm is this. It just has very complex proposal mechanisms. So you can imagine spaces that aren't connected and continuous, that you have to jump through the space to get places. Model selection problems is a very fascinating example. We'll study that soon. So basically everybody's just coming up with different proposals and nicknaming their algorithm differently. And sometimes it's highly computational how people come up with the proposed spaces. This is pretty simple in our case. The last step is I would just decide what to do. Let's say theta t is equal to theta star with prob alpha. This is 1 minus alpha. I stay in the same location. Same thing that we normally do. So that's how I code that thing up. I would not plug this in, this product right here. If I see e's, I get scared in my code. It's going to explode on me, and it will eventually. Cause me hours of grief. And products are pretty bad too. So, nice thing that you can do is you can make a log over all of that stuff. So sums are better to compute than products, and working with log likelihood functions is easier than working with likelihood functions. So I try to code everything up on a log scale. Let me show you my code. I haven't actually walked you through it. One thing I want to show you right before the code is I want to tell you what a Gibbs sampler actually does. This is what a Gibbs sampler does. And this is very easy to describe. So I'm going to make this just a 3-state or a 3-parameter system. So I'll just say, consider the distribution pi, theta 1, theta 2, theta 3. And if we want to make this seem like we're Bayesians, we'll condition on data. Okay, how did we get that distribution? I took the likelihood function that involved those 3 parameters, I wrote it down correctly, I multiplied it into my prior. I don't have any context for this right now, so I'm not going to pretend, but there's plenty of examples that we'll be studying where the context will be given to you. So there's some posterior and some likelihood function times some prior. So here's what a Gibbs sampler does, is you first sample theta 1. And I sample it from its full conditional distribution. Theta 2, theta 3. So this is the full conditional. I need to initialize this. So I'm going to come up with some initial values. So if there's 3 parameters, you need 2 initializers. If there's 17 parameters, you need 16 initializers. You need to initialize everything but the first step. So 0 step is initialize. And you're going to initialize those 2 things. I'm going to run this in a loop. This one, I'm going to update from its full conditional distribution. Theta 1, theta 3. And to make it look like we're Bayesian, we'll condition on x. Which values do I plug in here? Your most recent values. So this one gets plugged in here. I never needed to initialize it, but I've got a sample for it. This one is going to be our previous value that we initialized. Probably unsurprisingly, the third step is to sample from the third full conditional distribution. This is conditional on theta 1, theta 2, given x. Which ones do I use? My most recent values. That's what a Gibbs sampler does. So it samples iteratively from the full conditionals and plugs in your updated estimates all the way through. It's a lot of iterative matrix multiplying schemes or matrix solving algorithms that do something similar to this. Here's the surprising thing. If I don't know how to sample from those full conditional distributions, I can use Metropolis-Hastings. So it turns out that these are Metropolis moves in themselves. They correspond to having the full conditional being the proposal. That always leads to a Metropolis ratio of 1. I need to say that more to you. But Gibbs is pretty easy to implement. This is what most people do, is they'll break up a parameter space, and if they don't know how to sample from that distribution, they'll apply Metropolis-Hastings in the middle. I haven't proven to you that this converges, and I haven't proven to you that Metropolis-Hastings converge. But the math that governs their convergence is exactly the same. That's where the proofs will come in. Let me just illustrate in the last 2 minutes the code that we've looked at a number of times. Basically, I have a lot of initializing stuff, things that control the burn-in, how many iterations I want to run for. I'll tell you about this stuff later. But what I do is I break this into 2 blocks. I initialize everything. I make some plots so you can see everything. I've got my initialization. And then I have a lot of notes in this code right here. So it turns out I know how to sample from both of those steps. And I could implement a Gibbs sampler, or I could run the Gibbs sampler for estimating my precision and my mean parameter. And I should just be sampling those, but what I've done is I've slowed it down even further by using badly tuned Metropolis steps so that you could watch the convergence. On your new homework, you're supposed to do the same problem. And your problem will converge in 3 steps. And so that's a very bad example for me to show you for the first time, because the most important thing in MCMC is diagnosing whether or not you converge. And so these are both metropolized steps on the log scale. I've also coded it up in terms of the product scale, and I'll show you later this code failed miserably when I used those lines of code that are implemented the way that I wrote them down on paper. On the log scale, everything works great. So I've done the same thing here. We know that that full conditional is a gamma. We worked it out in the first week of class. I'm going to pretend I don't know that. I don't know how to sample for it. So I've also got some sort of Metropolis move right here. And I'll be posting this online, but a little bit later for you guys. So you can play around with it. Bad code for actually using, but it's good instructional. There is an error in this code. And I put a document up online that you can read through, and the document says you will not be able to detect my error unless you understand what the error is. So go and read through the document that I posted online, and it tells you actually how to set up a correct proposal for sampling fee. Conclude this lecture just by running everything one more time. This is the same thing that we saw before. I've started it very far away from the truth, and we see all the concepts come together. This is just a Markov chain. I've got some sort of proposal. And so my proposal is the algorithm. I'll tell you more about that when we go through everything. But this is the stationary distribution. This is the stuff that's non-stationary, right here. And then eventually, once it becomes stationary, it stays stationary. So that's how MCMC all comes together. Now, I know I've crammed a lot into 1 week. So I think we need to do more math in this class, get you ready for the midterm in 2 weeks, and then come back around to the math on all of this. The reason MCMC is the most popular algorithm ever, or however you want to say it, it's pretty popular, is it's easy to implement in Spirit. It's 2 steps, and it has vast utility to Bayesians, or anybody that's trying to sample from a distribution and they don't know how to do it. It's just that Bayesians, this was the tool that they were able to apply where they could finally stop arguing about philosophical concerns and say, look what I just need to do. And I think that that appeals to most of us. So we can solve more problems. So I tell Sierra all the time, I've got this tool, it might be slow sometimes, and I can speed it up later, but I can solve any problem. I can build any model, and I can estimate from any model, so long as I've got enough cores. And if I don't have enough cores, then I write a paper on a better proposal. And then I get a 2 for 1. That's my whole brief. Anyway, have a great fall break, and I'll see you guys hopefully tomorrow with review. Appreciate it.